A radio signal lasted 72 seconds in 1977, and no telescope has recorded it again. Dark matter shapes galaxies, yet roughly 27% of the cosmos is still described as invisible. In 2017, astronomers tracked ʻOumuamua, the first confirmed object from another star to cross our solar system. Beyond Neptune, an unseen planet has been proposed from orbital patterns, but it has never been seen. These cases are not equal. Dark matter has several independent lines of evidence. The WOW signal is a one-time event, and Planet 9 remains a testable hypothesis. Could these mysteries reveal new physics or only the limits of our measurements? The useful comparison is between what is measured, what is inferred, and what remains unresolved. The light we see from distant galaxies is ancient. It has traveled for millions, sometimes billions of years to reach our sensors. Every photon captured by a telescope is evidence from an earlier state of an object, not a live view of its present condition. We have mastered the art of observation. We can map the birth of stars and detect the faint ripples of gravitational waves. Yet, there is a profound difference between seeing something and understanding what it is. In cosmology, this distinction defines our reality. When scientists label an element as dark or mysterious, they are not using these terms to evoke wonder or fear. They are marking a boundary in the evidence. The measurements are real, the physical explanation is incomplete. That distinction matters because a name is not a detection. Consider the rotation of galaxies. The stars within these systems move at speeds that far exceed what would be expected based on visible mass alone. Many galaxies rotate faster than their gas, dust, and stars would predict, while their large-scale structure remains consistent with additional gravitating mass that does not appear to emit, absorb, or reflect detectable light. This is not magic. It is an observation that can be described with an additional mass component. We call that proposed component dark matter. The name does not identify its substance. It describes what our instruments have not detected. Its gravitational effects are measured, while its interaction with light remains undetected. It functions as an inferred scaffold. We cannot see the component directly, but its gravitational effect can be mapped through observations of ordinary matter. The evidence for this unseen mass comes from several observations, including galaxy motions, gravitational lensing, and the growth of large-scale structure. That evidence is strong, but it does not yet tell us what dark matter is. If the inferred mass were removed from the models, the observed motions and structures would no longer be explained by the same calculations. The distinction becomes important when two different problems appear together. A galaxy rotating faster than its visible mass predicts points toward the dark matter problem. An expansion rate that accelerates points toward dark energy. Neither observation is a calculation error. Each identifies a different boundary in our current explanation. We live in a cosmos whose visible material is only part of the total model. The stars and planets we photograph are the measurable surface of a system that also includes components we infer indirectly. If our understanding is limited by what we can see, then every anomaly becomes a data point. It tells us where to look next. Some discrepancies involve long-lived structures such as galaxies. Others are transient signals that appear for seconds and then disappear. If something invisible is influencing the large-scale structure, what should we conclude when a signal appears once and refuses to repeat? Is it an instrumental problem, a natural event, or evidence that requires another observation? The universe is not a static gallery. It is a dynamic system where some elements are constant and others are brief transients. These short-lived events show how much information can be missed when an observation is not repeated. In 2017, an object entered our neighborhood from outside it. It was not a rock born in this solar system. Its orbit did not belong here. This was the first confirmed interstellar object to pass through our gates, ʻOumuamua. Before that visitor, astronomers had also learned that the sky can change faster than a normal planetary image. Fast radio bursts, or FRBs, are brief flashes of radio emission that last roughly milliseconds. Some sources repeat, others have been seen only once. Their astrophysical origin is now the subject of active research, but a flash is not automatically a message. One earlier event still carries that warning. On August 15, 1977, Ohio State University's Big Ear telescope recorded the WOW signal, a strong narrow-band event that rose and fell across the telescope's beam in about 72 seconds. Follow-up searches did not detect it again. It is an unresolved observation, not evidence by itself of extraterrestrial intelligence. It moved through the solar system on a hyperbolic trajectory, carrying limited data from another star system. Because it was faint and visible for only a short time, we were left with fragments of its identity. Its brightness changed as it tumbled, and its path showed a small non-gravitational acceleration. The cause remains debated. Outgassing is one natural explanation, but the observations do not establish propulsion or an artificial origin. To this day, the question remains, what was it? A fragment of a shattered planet? An icy body venting gases? Or another natural object that our short observation could not classify? Because we had no time to send a probe or capture high-resolution imagery, ʻOumuamua became a measure of our observational limits. It demonstrated that interstellar objects can pass through our system, not that we already know how such objects form. While ʻOumuamua was an intruder passing through us, another hypothesis lies at the edge of our home. This is Planet 9. It has never been directly observed. The proposal comes from claimed patterns in the orbits of distant bodies beyond Neptune, which some researchers interpret as evidence for the gravitational influence of an unseen planet. The planet, if it exists, would orbit so far away that finding it against millions of background stars is difficult. But the inference is not a discovery. Observational bias and alternative explanations remain part of the scientific debate, so Planet 9 is best presented as a testable hypothesis rather than a missing world already on the map. The local cases lead to a different kind of measurement, the first light released by a cooling universe. This is the cosmic microwave background, the oldest map we have of the early cosmos. But on this ancient map, there is an unusual temperature pattern known as the CMB Cold Spot. The feature is real in the map, but its interpretation is not settled. The measured anomaly is not itself evidence that current physics has failed. Studies have examined where the foreground structure, including a large underdense region, sometimes called a supervoid, could explain part of the signal. That possibility is not proof of new physics, and the cold spot is not evidence that bubble universes collided with ours. More speculative proposals include cosmic textures or other physics beyond the standard model, but those are possibilities to test, not established explanations. The cold spot is therefore a useful example of the difference between an anomaly in data and a confirmed failure of cosmology. These cases, the visitor from another star, the proposed planet beyond Neptune, and the CMB temperature anomaly are not equivalent discoveries. They are indicators of different limits in observation, inference, and interpretation. The practical question is why these unresolved measurements demand attention when they are so far away or move so quickly. One answer begins with a fundamental asymmetry. For us to exist and observe this data, the early universe retained more matter than antimatter after their near-symmetrical production and annihilation. Matter dominates over antimatter by a very small margin, and the mechanism that produced that asymmetry remains unresolved. If matter and antimatter had remained perfectly balanced, their annihilation would have left far less material from which stars and planets could form. The observed excess of matter is therefore a condition of our existence, while the physical mechanism behind it is still an open problem. The same reasoning applies to the search for other civilizations. A universe that could contain many signal-producing worlds has produced no confirmed transmission for us, and that result is still shaped by distance, time, and instrument sensitivity. If the Great Silence persists, is it because we are alone? Or is it because a civilization could occupy a region of space-time we have not learned to observe? The absence of a confirmed signal sets a limit on what we can currently conclude. It does not answer the question by itself. If we are seeing only what falls into a narrow window of perception, how much information remains outside the range of our current instruments? The discovery of exoplanets has fundamentally altered the math of solitude. In previous decades, it was possible to argue that Earth-like worlds were rare anomalies, statistical flukes in a mostly barren galaxy. That argument is no longer viable. The universe produces diverse planetary systems with extraordinary frequency. We now know the cosmos is teeming with variety, from rocky terrestrial planets and gas giants to super-Earths orbiting small, long-lived stars. The ingredients for potential habitats are no longer a mystery, they are common. We have mapped thousands of these worlds in our immediate neighborhood alone. This realization does not make the silence easier to bear. Instead, it makes the lack of signal more profound. The problem is no longer a shortage of locations. It is an absence of voices. When we look at this great silence, we are forced into a series of analytical interpretations regarding why our telescopes return only static where there should be conversation. Why do the worlds exist, but the signals remain absent? There are several technical and logical hurdles to consider. First is the window of detectability. A civilization might utilize radio waves for a brief period, a mere century or two before transitioning to technologies we cannot yet conceive, or methods that do not radiate outward into space. In this scenario, their voice would be like a spark in an ocean, present only for a moment before it is swallowed by the scale of time and distance. Then there is the matter of physical barriers or biological limitations. A civilization may exist, but its form, whether organic, synthetic, or something else entirely, may not produce a signature that falls within our definition of signal. If its observable effects differ from our assumptions, we might not recognize them as evidence of life. This leads us to one of the most sobering frameworks in modern cosmology, the Great Filter. This is not a narrative about monsters or cosmic barriers, but an interpretation of probability and survival. It suggests that there may be a barrier, a filter that makes it extremely difficult for a civilization to survive long enough to become detectable across interstellar distances. The Great Filter proposes that the scarcity of signals is due to civilizations failing at certain developmental stages. If this filter lies in our past, if we have already passed through it by developing high-level technology and sustaining a society, then we are a rare, precious anomaly. We would be alone in much of our history. However, if the filter lies ahead, it suggests that many civilizations may rise to our level only to encounter self-destruction or environmental collapse before they can reach out into the stars. This isn't an attempt to predict doom, it is a way of mapping the probability of our own existence. Every answer we find regarding why the cosmos remains quiet changes how we view ourselves. If we are alone, then the responsibility of consciousness becomes immense. We may be the only eyes through which the universe can witness its own majesty. The Fermi paradox is not only a search for other civilizations, it is also a test of what our observations can establish. The matter-antimatter problem shows why our own existence is part of the evidence. At this point, the important question is not which mystery sounds most dramatic, but what evidence could change the conclusion. For dark matter, a direct interaction with ordinary matter would reveal more about its physical nature. Until such a detection exists, gravitational maps remain powerful evidence for an unseen component, not a sample we can place in a laboratory. For fast radio bursts and the wow signal, a repeat observation from an independent instrument would be more informative than a stronger description of the first event.
Repetition can separate a persistent source from interference, a transient natural event, or a one-time error. ʻOumuamua cannot be revisited with the data available from its short passage, but future interstellar objects could provide a larger comparison set. If several visitors show related properties, scientists can test whether the first object was unusual or representative. Planet 9 faces an even more direct test. A survey can search the predicted sky and either find the object or narrow the region in which it could exist. A non-detection would not prove the hypothesis false immediately, but it would constrain its allowed versions.
The cold spot can be tested by comparing maps at different frequencies, modeling foreground structure, and asking whether the anomaly remains statistically unusual after those corrections. The matter-antimatter problem is approached through particle experiments and cosmological observations that measure how much asymmetry known physics can produce. And the great silence changes only when a candidate signal is repeated, characterized, and independently confirmed. This is the common thread. A scientific mystery becomes progress when a new measurement can distinguish between competing explanations. Until then, the responsible conclusion is not certainty or dismissal, but a precise description of what the evidence does and does not show. The cases are not a catalogue of supernatural claims. They are different tests of the same boundary. Dark matter is inferred from gravity, transient signals are measured but hard to interpret, and Planet 9 and the cold spot remain hypotheses or anomalies under active study. The Great Silence adds a different limit. The absence of a detection cannot by itself prove that no one is there. We are standing on a small island of observation in a massive ocean of data. The useful lesson is not that the universe is hiding its secrets, but that every instrument has a limit. A reliable anomaly tells us where to look next. It does not tell us which explanation will win. The universe is not silent because it has nothing to say. We are still learning which measurements can distinguish a signal, an anomaly, and an